Hello everyone, this is Vishu Chaudhary from Infinity Vision. I'm a chemistry faculty over here. So today I will provide you the detailed solution of JEE Main 2024 January session, and the date is 30th Jan, shift to chemistry paper. So let us start with the solution part. The first question is, which among the following purification methods is based on the principle of solubility in two different solvents? Let's look through the options. The option A is column chromatography, then we have sublimation, distillation, and differential extraction. Now this question is quite simple. It is based upon NCERT theory only. Now chromatography, as we know, it is used to separate the components of a mixture, testing their purity, and column chromatography is a type of adsorption chromatography where the principle is adsorption. So this is not the option. Sublimation is used to separate the sublimable substances like naphthalene, camphor from non-sublimable impurities for say sand. So this can't be the answer. Then we have distillation. Now distillation is used to separate liquids which have significant difference in their boiling points, or liquids, volatile liquids basically, from the non-volatile impurities. So this is also not the answer. Now differential extraction is a technique where, suppose if we have an organic compound in the aqueous medium is separated by shaking it with an organic solvent in which it is more soluble. So here the principle of solubility comes into picture. So this is the answer. So differential extraction is the purification method based upon the principle of solubility. So let us discuss the next question. Okay, so next question, we know that it is one of the most important reactions of phenol. Now, salicylaldehyde is synthesized from phenol when reacted with, so like I said, we all are aware of this reaction, that is Reamer-Tiemann reaction. Now, it is basically the orthoformylation of phenol where CHO group is introduced at the ortho position. So if we see the fourth option, which is the correct one, so these are the reagents. So we have the phenol in the presence of chloroform and a strong base for say KOH. What we get is your orthosalicylaldehyde like this. And why ortho is the major product over here? Because of the intramolecular hydrogen bonding possible. So this is your orthosalicylaldehyde. Now, two or three important points about this reaction. The first one is the intermediate. So the reaction is followed by, we have the carbene intermediate, because CHCl3 in the presence of KOH, we get a carbanion first of this sort, and then the removal of one of the chloride give rise to dichlorocarbene, which is the intermediate over here. Now, this dichlorocarbene is the electron deficient species. So the electrons of this phenol ring will attack over here, and ultimately what we get is salicylaldehyde. So this is from Reamer-Tiemann reaction. Again, a simple question based upon NCERT theory only. So let us discuss the next question. The question is, given below are two statements. Statement number one is high concentration of strong nucleophilic reagent with secondary alkyl halides which do not have bulky substituents will follow SN2 mechanism. And statement number two says a secondary alkyl halide when treated with a large excess of ethanol follows SN1 mechanism. Okay, so we know that in the SN2 reaction, the rate of SN2 reaction depends upon the concentration of both, that is the substrate alkyl halide molecule and also the nucleophilic reagent, right? So the higher the concentration of a nucleophilic reagent will definitely increase the rate, and hence it will follow the SN2 mechanism. Also, it says that the secondary alkyl halides which do not have the bulky substituents. Now we know that in SN2 reaction, the nucleophile should have enough space or access to the sigma star orbital between the carbon and the leaving group. So So yes, so the substrate molecule should not have sterically hindering substituents on it. So yes, we should have the lesser, bulkier substrate molecule in the SN2 mechanism. So this statement is correct. Now statement number 2 says a secondary alkyl halide when treated with a large excess of ethanol. Now ethanol being a polar protic solvent, it is also a nucleophile, right? So, and we know that this polar protic solvent, what it does in SN1 is the polar part stabilizes the unstable carbocation intermediate formed in the SN1, and the protic part helps in the solvation or solvolysis of the leaving group or the negative part, that is the halide part. So yes, in the presence, so basically solvolysis is favoring this SN1 mechanism. So this is also correct, right? So both these statement 1 and statement 2 are correct. So statement 1 is true. Both these are true. So fourth is the right answer. Both these statements are correct, right? Let us move to the next question. So this is question number 4. Metachlorobenzaldehyde on treatment with 50% KOH solution yields. Now, this is also based upon NCRT theory. This reaction is Cannizaro's reaction, again a name reaction from the carbonyl compounds. Now, we know that carbonyl compounds which are not having alpha hydrogen, they basically, it undergoes disproportionation in the presence of a strong base, and one of the molecule gets oxidized to the corresponding acid part and the other molecule gets reduced to the corresponding alcohol moiety. So basically we have the metachlorobenzaldehyde. So we have the metachlorobenzaldehyde. Right. Now if we have the benzaldehyde, we know that there is no alpha H, right? So in the presence of a strong base, one of the molecule gets oxidized to the acid part, corresponding acid part, that is CO minus. Now, since this is in the presence of a base, so obviously we get carboxylate anion, right? So A cannot be the answer, right? And among second, third, and fourth, here we have the, no, this OH cannot come into picture. Similarly, this, so we are left with just one option, and this is absolutely correct, that one of the molecule of this metachlorobenzaldehyde gets oxidized to this carboxylate ion, and the other is reduced to the alcohol part. Now, some important points about this reaction. Basically, like I said, this is a disproportionation kind of reaction. And if you see the mechanism, basically there is a step in which there is a intermolecular hydride transfer, right? So let me show you some mechanism part, like if not the fully part. If not the full mechanism, let us discuss something. The first step is the attack of this OH minus on the carbonyl, right? What do we get is this type of anion, right? And the next step is very important because the next step leads to the reformation of the carbonyl compound. It leads to the reformation of the carbonyl compound, and this hydride is transferred to the another molecule of the carbonyl compound, right? So this is how the mechanism goes. So basically second is the right answer. So let us discuss the next question. So let us discuss this question. Given below are two statements. One is labeled as assertion A and the other is labeled as reason R. Assertion is H2TE, that is hydrogen telluride, is more acidic than H2S, that is dihydrogen sulfide or hydrogen sulfide. Now, reason is the bond dissociation enthalpy of H2TE is lower than H2S. Now, this question is self-explanatory. Basically, both are correct. Assertion is correct and reason is the correct explanation of this assertion. So, first of all, yes. Why? Because we know that as we go down the group, the size of the atom goes, it becomes larger and the overlapping is poorer. The bond enthalpy for the dissociation of this hydride is less down the group. So yes, the bond dissociation enthalpy is lower of hydrogen telluride is lower than hydrogen sulfide because the bond is weak. And we know that the bond strength is inversely proportional to bond length. Down the group, this overlapping is poorer, the bond length increases, and the bond strength decreases. So this is self-explanatory, right? A very simple question. Let us discuss the next question. Question number 6. Now this is also not difficult. We know that this B is hydroboration oxidation, and this A is, hydration of alkene in the presence of acid catalyzed hydration. So let us discuss this question. Now, for the hydroboration part, we know that hydroboration takes place in the anti-Markovnikov manner. So we add OH in accordance with the anti-Markovnikov rule. So what do we get here is this, right? What do we get? The B is this type of molecule. Now, some more points about hydroboration oxidation is that hydroboration oxidation is a stereospecific reaction where the BH3 acts in the syn fashion, right? That BH2 and H, they are added on the alkene from the same side, and leading to the formation of trialkyl borane, and in the second step oxidation, where the boron is replaced by the hydroxyl. So basically, we can remember that this reaction is accompanied with respect to the anti-Markovnikov rule. And this is simple. This is followed by the carbocation intermediate. So wherever the more stable carbocation is formed, there the OH minus will add. So we know that when we split this double bond, we need to get positive over here because this is 3-degree carbocation, which is definitely stable if it would have been here. So what do we get is, this is the product. So A is this and B is this. So please see, they have given A this side. So don't get confused while marking. So this is A. So this is A and this one is B. Yes. So second is the right answer to this question. Not at all. I mean, it is not difficult at all, right? It's also very simple. Let us discuss the next question. Now, this is IUPAC from the IUPAC nomenclature. Let us discuss this. So basically, this is your carbon-containing functional group. So obviously, the numbering will start from this nitrile part, 1, 2, 3, and 4. So the name is 3-amino, because this is your amino group, and 1, 2, 3, 4 butane nitrile. So 3-amino butane nitrile. Third is the right answer. Quite simple, right? Let us discuss the next question. So let us discuss the next question. Question number 8. Okay. So in the first step, I think there is nitration of benzene. So concentrated HNO3 and concentrated H2SO4. So the first step is your nitration of alkene. It leads to the formation of nitrobenzene, and nitrobenzene gets reduced by SnHCl or FeHCl to amine. So what is A? A is aniline. A is aniline, and what we get from the first step is nitrobenzene, and nitrobenzene gets reduced by tin or HCl, tin HCl and FeHCl to aniline. Now this is diazotization reaction. So what do we get from the first one is diazotization reaction. What we get is benzene diazonium chloride salt, and the next part is your azocoupling. The next part is your azocoupling. So that the position which is trans to phenol gets coupled with the benzene diazonium salt, and what do we get is a dye which is an orange colored dye, para-hydroxybenzene. So this is the right answer. We get aniline in the A part and para-hydroxyazobenzene here. This is, we know that this is your azo group, and this is your orange colored dye. Again, a question from NCERT theory, right? Let us discuss the next question. Okay, the molecule or ion with square pyramidal shape. Okay, if we see the first option, we know that nickel here is 3D8 system, right? Nickel is in +2 oxidation state. So Ni2 plus is 3D8 system. So if we see, this is S. So if we see, this is 3D, this is 4S, this is 4P, and cyanide is a strong field ligand. So obviously it will 5, 6, 7, 8, and cyanide is a strong field ligand. It will pair up the electrons. So this will paired up, and what do we get is DsP2 hybridization, right? DsP2 hybridization. So so this is square planar geometry. So A cannot be the answer. If you see B is simple. This is trigonal bipyramidal, right? Same goes for fourth. It is also trigonal bipyramidal. Now, if we see the third option, let us discuss the bromine. So if we see the total valence electron count of bromine, that is 7. So 1, 2, 3, 4, 5, 6, 7. And there are 5 fluorines, so 5 bond pairs, 5 bonds with fluorine. What do we get is 1 lone pair. So basically there are 5 bond pair and 1 lone pair, the steric number being 6. So the electron geometry is octahedral, but the molecular geometry is square pyramidal. Like this. The square geometry or the molecular geometry or the shape is, and there's 1 lone pair like this. So this is the square pyramidal geometry. So BRF5 is the right answer to this question. Clear? Let us discuss the next question. The orange color of potassium dichromate and purple color of potassium permanganate is due to, okay. Now we know that chromium in potassium dichromate is in +6 oxidation state. This is D0 system. Also, manganese in KMnO4 is in +7 oxidation state. That is the highest oxidation state possible. Again, this is D0, right? So DD transition is definitely not possible. So let us eliminate. DD transition possible? No. DD transition? No. DD transition? No. We are left with just one answer, that is charge transfer in both, or charge transition in both. Now what happens in charge transition? Basically we have the vacant high energy orbitals in the case of metal, and we have the oxide. Oxide is a ligand with low energy filled orbitals, so there will be a transfer of electrons from the ligand to the metal empty orbital. So this is so both of them are colored due to LMCT. That is ligand to metal charge transfer. Clear? So this is the first one is the correct answer. Let us discuss the next question. Okay. Next question is alkaline oxidative fusion of MnO2, that is pyrolusite ore, gives A, which on electrolytic oxidation in alkaline solution produces B. A and B respectively are. Okay. The first one is the preparation of, basically this is one of the reactions involved in the preparation of potassium permanganate. So MnO2 alkaline oxidative fusion means we have KOH, we have O2. This gives rise to, potassium manganate. This is dark green. This is dark, plus H2. This is dark green. So we have MnO4 2 minus, that is manganate ions as A. Now these manganate ions, upon electrolytic oxidation, so basically what we have that at anode, what kind of reaction is taking place? At anode we have the manganate ion losing one electron and getting converted to MnO4 minus, right? So MnO4 minus, that means manganate ions getting converted to permanganate ions. And what is happening at the cathode? Basically alkaline electrolytic oxidation in alkaline solution. So what do we have? Like we have water. So what will happen? It will take up this electron getting converted to half H2. So H2 is released at the cathode, and we have OH minus. And this OH minus will combine with alkaline. So it will combine with, like, for say K plus, it will give rise to KOH. So basically we are concerned about this, that MnO4 2 minus loses electron on electrolytic oxidation and gets converted to the permanganate ion. So if we go by this, then second is the right answer. Clear? All right. Let us discuss the next question. If a substance A dissolves in solution of a mixture of B and C with their respective number of moles, then mole fraction of C in the solution is, now we know that mole fraction of any substance is equal to the moles of that substance divided by the total number of moles. So if we are asked to calculate the mole fraction of C, or to tell what is the mole fraction of C, then it will be the moles of C divided by the total number of moles, that is moles of A plus moles of B plus moles of C. So going by that, second is the right answer. This is just the definition of mole fraction. Clear? Let us discuss the next question. The next question is again statement type question. So let us see. Statement number 1 is, along the period, the chemical reactivity of the element generally increases from group 1 to group 18. Now this question is not even from class 11th or 12th. This is, we started this in junior classes only, like 9th or 10th. We know that along the period, the chemical reactivity does not follow a regular trend. It first decreases in the case of metals and then increases in the case of non-metals. And what is chemical reactivity? Is nothing, it is a tendency of losing electron or gaining an electron, right? So obviously in the case of metals, it will decrease from going from left to right, and then in the case of non-metals, it will increase. For example, we know that the reactivity, if we take the example of third period, then the reactivity decreases till silicon, right? And if we see from phosphorus to chlorine, definitely the reactivity will increase, right? So this statement is wrong. Second, the nature of oxides formed by group 1 element is basic, while that of group 17 elements is acidic. Again, from junior classes. Yes, group 1 for say Na2O, we know that when we write reaction of this with water, we get NaOH, which is a strong base, and group 17 for say Cl2O7, which on reacting with water give rise to perchloric acid. So yes, this is absolutely correct. The nature of oxides of group 1 is basic. So statement number 1 is false, but statement number 2 is true, right? Very simple question. Let us discuss the next question. The coordination geometry around the decacarbonyl dimanganese 0. Now this is a binuclear carbonyl compound. So basically, it's already mentioned in NCERT that the two square pyramidal units are joined together by M bond, right? So right. So this is your, and they are asking you the coordination geometry around the manganese. So if you see around the manganese, the coordination geometry is octahedral. It is quite visible. The coordination geometry is octahedral. They are asking you the coordination geometry around manganese, right? Around manganese in decacarbonyl dimanganese. So it is octahedral. All right. Let us discuss the next question. Okay. Statement number 1. Since fluorine is more electronegative than nitrogen, the net dipole moment of NF3 is greater than NH3. All right. And the statement number 2 is, in NH3, the orbital dipole due to the lone pair and the dipole moment of NH bond are in opposite direction, but in NF3, the orbital dipole due to lone pair and dipole moment of NF bonds are in the same direction. So if we see NH3, first of all, we should be knowing that both are polar, right? Both are polar molecules. But if you see the direction of dipole moment, then obviously it is towards N and it is towards the lone pair. So basically, the the orbital dipole due to lone pair and the dipoles due to these bonds, they are in the same direction. So mu of NH3 would definitely be greater than NF3 because there is some sort of cancellation, right? There is some sort of cancellation in the value of mu. So if we see the dipole vector of the lone pair and the bonds, they are in the same direction in NH3. So mu is more than, mu in NH3 is more than mu in NF3, but it is saying that, it is saying the reverse, right? So statement number 1 is false. And the second, it says that in NH3, the orbital dipole due to lone pair and the moment of NH bonds are in opposite direction. No, they are in the same direction. That is why the mu of NH3 is greater. So this is also incorrect. So both of the statements are false. So second is the right answer. Clear? All right. Let us discuss the next question. The correct stability order of carbocations. Now this is very simple. In fact, this is of the NEET level. We know that if you see the hyperconjugative structures, we say that more the number of hyperconjugative structures, which further depends upon the presence of alpha H on the sp3 hybridized carbon, more will be the stability of the carbocation. So this is again self-explanatory. If you see the third part, if you see that the number of alpha H keeps on decreasing from A to B to C to D, and so is the stability order of carbocation, right? So this is quite simple. Now, if you are confused with alpha H, let me tell you, like for example, if we have something like CS3, CH2 positive, then this is your alpha carbon, this is sp3, and the H attached to this alpha carbon are alpha H. So basically there are 3 alpha H. So more the number of alpha H, more will be the hyperconjugative structures, and hence more will be the stability. All right. So this is simple. Let us discuss the next question. All right. The solution from the following with highest depression in freezing point, lowest freezing point is, okay. So basically we know that if we see delta TF, that is depression in the freezing point, it is, we know that it is directly proportional to the value of want off factor into M, that is the molality. So let us calculate I and M in all of these. So if you see the first one, let me show you just one. 180 gram of acetic acid dissolved in water. So for the first one, if you see molality, let us consider all the solvents are 1 kg. We are taking it in the 1 kg. All right. So molality will become 1. Molality will be given mass upon molar mass, that is 60 for acetic acid. So it gives 3. And what about I? Now acetic acid in water, we know that it dissociates in water. So basically acetic acid dissociates in water. It dissociates in water. So if I say, what is the value of, so see, basically I will definitely be greater than 1 in the case of acetic acid. We can calculate I in this manner also, that it is the total number of moles after dissociation, that will be 2, right? And total divided by the total number of moles before, that is 1. So it is greater than 1. Right. So if you put the value over here, so we will see that in the first one, the product of this I into M will be maximum, right? And hence the first one will have the highest depression in the freezing point. Now we can do it in another way also, because we know that delta TF is Kf into I into M, where Kf is the molar depression constant, and the value of Kf for water and benzene both are given in the NCERT. For water, it's 1.86 kg Kelvin per mole, and for benzene it is 5.12 kg Kelvin per mole. So even if you put the values of Kf, we can get the answer, right? In the last one, we know that I is equal to 1 because this is a non-electrolyte, right? So this way we can calculate, and the first will be the right answer. We will get delta TF will have the maximum value in the case of first one, and hence the lowest freezing point. All right. So let us discuss the next question. The next question is A and B formed in the following reactions are, okay. So we have chromyl chloride on the reaction with NaOH. What do we get? We get yellow colored compound, which is sodium chromate, right? Plus NaCl plus H2O. Now sodium chromate on reaction with HCl, which is A, in the presence of H2O2, it gives rise to, we get chromium 6 oxide, that is CrO5. This is unstable. This is blue colored compound. This is unstable and blue colored compound, plus NaCl will be there, plus H2O will be there. So B is basically, we are concerned about this, CrO5, that is chromium 6 oxide. And what is the structure? Structure is also important. It is the butterfly structure, butterfly type structure, where this has two peroxide linkages like this. So if you see the oxidation state, -2 and -1, -1, -1, -1, so it will be +6. So chromium 6 oxide, clear? So A is the right answer. A is the right answer. Let us discuss the next question. Choose the correct statements about, again, the question based upon hydrides, this time group 15 hydrides. The stability of the hydrides decreases in the order NH3, PH3. This is again self-explanatory as we go down the group. The bond strength decreases, the bond enthalpy decreases, and hence the thermal stability also decreases. So this is correct. The stability of the hydrides decreases in this order. Yes, this is absolutely correct. The reducing ability. The reducing ability is the ability to release H of the hydrides increases in this order. Now weaker the bond, more easily it will be for the hydride to release H. So this is again true. This statement is also correct because in the BiH3, the bond is the weakest, bond strength is the lowest, and hence the release of H will be most facile in BiH3. Let us see the C option. Among the hydrides, NH3 is a strong reducing agent while BiH3 is mild reducing agent. It is contradicting the second statement, so this is incorrect. The basicity increases in this order. Okay. So basically, let me take example of first two, NH3 and PH3. Now basicity means that we need to donate this lone pair of electrons. Okay. Now, in the case of NH3, this lone pair of electrons is located in a smaller volume. It is accommodated in a smaller volume. Whereas as we go down the group, that there's a dispersal of lone pair and hence the basicity decreases, right? There's a dispersal of lone pair, whereas here this is kind of localized thing, or it is accommodated in a smaller volume. It is concentrated, but here it is dispersed over the entire volume. Right? So the basic strength decreases, but it is saying that the basic strength increases. So this is also wrong. So the correct statements are A and B. So A and B are the correct statements. Clear? All right then. Let us discuss. So the question is, reduction potential of ions are given below. We have perchlorate, periodate, perchromate, and the standard electrode potentials are given, or the standard reduction potentials. Now, we know that higher the value of standard reduction potentials, more will be the tendency to undergo reduction, right? And hence more will be the oxidizing power. So if we go by that, here the SRP value is higher, so it has the maximum tendency to undergo reduction, and hence it has the most oxidizing power. So followed by this and then this. So B is the right answer, right? B is the right answer because it is having the highest value of SRP. So more will be the oxidizing power. All right, let us discuss the next question. Coming to section B, all right. Number of complexes which show optical isomerism among the following. So this question is from the coordination isomerism. Okay, now we know that suppose if we have a bidentate ligand of AA type, right, we can have this possibility in the octahedral geometry, and we can have this possibility, let's say A2. This is monodentate, these are bidentate. Now, in the case of when all three are the bidentate ligand, we know that each bidentate ligand is perpendicular to each other. So in the case of MAA3 type, there can never be the plane of symmetry because these bidentate ligands, all the three bidentate ligands, they are perpendicular to each other, right? They are perpendicular to each other, so there cannot be POS. So yes, this is always optically active. So if we see this, this is always optically active. In the case of trans, if we see this, in the case of trans, geometry, there is always a plane of symmetry, right? So in the compound of MAA2, where AA is your bidentate ligand and small a is your monodentate ligand, the trans isomer is always optically inactive. So this cannot be optically active, this cannot be optically active. Now, in the case of cis, now again, in the case of cis, this bidentate ligand, they are perpendicular to each other. If they are at cis, they are at 90 degree perpendicular to each other. They can never be POS. So in the case of 3 bidentate ligands, and even in the case of 2 bidentate ligands, they cannot be the plane of symmetry, right? So this is optically active, this is optically active, and cis, again, oxalato, again, optically active. So there are 4 such compounds or complexes which can show optical isomerism. So the answer is 4. But the trans form, they are optically inactive. All right? Let us discuss the next question. The question is, NO2 required for a reaction is produced by decomposition of N2O5 in CCl4 as by the equation this. The initial concentration of N2O5 is 3 moles per liter and it is 2.75 moles per liter after 30 minutes. So we know that the rate of reaction can be written as the rate of disappearance of the reactants, that is minus d of N2O5 upon dt. And we also take into consideration the stoichiometry. So this will be minus 1 upon 2. That can be written as the rate of appearance of the products. Again, the stoichiometry is taken into consideration. And same goes for O2. That is d of O2 upon dt. Right? So we need to find out the rate of formation of NO2. That means we are supposed to find out dNO2 upon dt, the rate of formation, right? So if we see by this, we can write dNO2 by dt as, if I take 4 this side, so this will be minus 4 upon 2, that is minus 2 into d of N2O5 upon dt. Now this small change in the concentration of N2O5 is given, that is, it was 3 initially, and after 30 minutes it is reduced to 2.75. So it can be written as 2.75 minus 3 divided by 30 minutes, that is 30. When you solve it, we will get 1.667 into 10 to the power minus 2, right? Moles per liter per minute. But we are supposed to give the answer in the of the sort x into 10 to the power minus 3. So I can write this as 16.67 into 10 to the power minus 3, or I can write 17 into 10 to the power minus 3. So the x value is 17. All right. So it is again an easy question from the chemical kinetics. Let us discuss the next question. Okay. 2 reactions are given below. We are given their enthalpy change also. Then you are supposed to find out the enthalpy change for the following reaction. Now this question is from the Hess's law of constant heat summation. So basically this is a required reaction, right? In this required reaction, we have Fe on the product side. So what we can do we can reverse the first reaction. If we reverse the first reaction, it will become 2 of Fe solid plus 3 upon 2 O2 gas. And on reversing the reaction, the delta H0 value is also reversed. So from minus to 822, it will become plus 822. And the second reaction, See, we need 3 carbon, right? So what we can do is we can multiply the second reaction by 3. If we do so, we need to multiply with the same coefficient over here. So what do we get is minus 330. And then you see that if we, this is your A, so this is a new reaction A, and this is a new reaction B. And when you add the two, you will get the required reaction. And if we are adding these two reactions, we need to add these delta H naught values also. So 822 minus 330, what do we get? Right? What do we get? So this will be 2, and 12 minus 3 is 9, and 7. So 492. So what is the answer? The answer is delta H naught value for the given reaction is 492 kilojoule per mole. So this is the answer, 492 kilojoule per mole. All right. Let us discuss the next question. Question number 24. Now this question is from NCERT, directly from the NCERT, where we have the biological functions of the nucleic acids. RNA is regarded as the reserve of genetic information? No. DNA is regarded as the reserve of genetic information. DNA molecule self-duplicates during cell division? Yes, absolutely correct. DNA synthesizes proteins in the cells? No. RNA synthesizes proteins in the cell. So this is also wrong. This is wrong. The message for the synthesis of particular proteins is present in DNA. Yes, RNA synthesizes proteins, but the message for the synthesis of particular protein is present in DNA. Absolutely correct. And identical DNA strands are transferred to the daughter cells. This is also true, based upon the NCERT theory. So we have 1, 2, 3. 3 statements, the total number of correct statements. So we have 1, 2, 3 statements correct. So these are the 3 statements. 1, 2, 3. All right. Let us discuss the next question. The next question is the pH from ionic equilibrium, the famous Henderson-Hasselbalch equation, which says that pH is equal to pKa plus log of salt concentration upon conjugate acid concentration. So the pH of an aqueous solution of containing 1 molar benzoic acid, where the pK value is also given, and 1 molar sodium benzoate, that is the salt, is 4.5. So this pH value is given 4.5. pK value is 4.20. And what you are supposed to find out, the volume of the benzoic acid solution in 300 ml of this buffer solution. All right. So 4.5 is equal to 4.20 plus log of salt concentration upon acid concentration. So basically, if I take this 4.2 this side, so it will be 0.3, right? 0.30. That is log of salt concentration upon acid. Now this is log 2. So I can write salt concentration upon acid concentration to be 2. All right. Now, so concentration is moles upon volume. So we can find out the moles. So we know that moles is concentration into volume. So if I find out the moles of salt, that will be concentration is 1. And volume, let us say it is Vs. And for Va, that is acid, we can write, again, the concentration is 1 molar. And let's say the volume is Va, right? So salt upon acid, what I can write is, I can also write this as volume of salt upon volume of acid is equal to 2. And now volume of salt is equal to 2 into volume of acid. And the total volume is 300. So Vs plus Va is 300. So I can say that 3 into Va is 300. So Va comes out to be 100 ml. So 100 ml is the volume of benzoic acid solution, which is present in 300 ml of this buffer solution. All right. So the answer is 100 ml. Let us discuss the next question. Okay. Number of geometrical isomers possible for the given structure. Now this is the only question which I felt is a good question, right? Let us see. So there are 3 alkenes. Now see, let's say there are 3 alkenes. This is A, this is B, and this is C. So A, B, and C. Now we know in order to exhibit geometrical isomers, suppose if we have the alkene of this type, A, B, and we have C and D, then we know in order to exhibit GI, these A and B should not be equal, and same goes for C and D. Now here, if we see the middle alkene, if these two alkenes are both are E or both are Z, then the middle alkene will not exhibit GI. Why? Because both these groups are same, so it will not exhibit GI. So what I'm saying is, if the first one is E and the last one is also E, then this will not exhibit any GI, right? And same goes for Z. If this is Z alkene and this one is Z alkene, this will not undergo or exhibit GI. Now it can exhibit GI if these two are either EZ or ZE, right? So what I can say is, suppose first one is E and the last one is, the C one is Z. So this can be E or this can be Z. So it will exhibit GI if the one of the alkene is E and the other is Z, right? So there are 4 possibilities. So number of geometrical isomers possible for the given structure is 4, because there are 4 such possibilities. But please remember, in 2 of them, the middle alkene will not exhibit GI. Clear? All right, let us discuss the next question. Total number of species from the following which can undergo disproportionation reaction. All right, we know H2O2 is unstable. It decomposes, and this decomposition is disproportionation type reaction. It decomposes into water and oxygen. Then chlorate. We know that this chlorate, in the presence of a base in the basic solution, it disproportionates into halide ion and the perchlorate ion. So again, a disproportionation reaction. What is a disproportionation reaction? The same species is getting reduced and oxidized. Now, if you see P4, very, very important reaction. In fact, we know that this reaction in the presence of a base, and we take H2O. What do we get is PH3, right? This is PH3, plus we get H2 PO2 negative. That means dihydrogen hypophosphite ion. So P4 dissociates, disproportionates into PH3 and dihydrogen hypophosphite ion. If you see Cl2, okay. If you see Cl2, then Cl2 also, we know this reaction Cl2, the reaction of Cl2 with NaOH. In the presence of NaOH, it disproportionates into, we know, it disproportionates into Cl minus plus ClO minus, right? So this is also a disproportionation reaction. And if you see Cu2 plus, now copper, this cuprous ion is unstable in aqueous solution, so it disproportionates into, it disproportionates into copper solid, where it is 0 plus copper cupric ions, copper 2 plus. Regarding NO2, NO2 also, upon hydrolysis, what do we get? We get HNO3 plus HNO2. This is again an example of disproportionation reaction. 5, 6. So these 6 species undergo disproportionation reaction among these. So 6 is the right answer. Clear? All right, let us discuss the next question. Number of metal lines characterized by flame test among the following is. Now, if you follow the NCERT book for the qualitative analysis, there it is mentioned that the chlorides of some metals, they undergo flame test. They have the characteristic flame color. Now, flame test, what is the principle? Principle is electronic transition and photo emission. So there it is mentioned that strontium ions, yes, they have the reddish color. Yes, they have the reddish, crimson red, in fact, crimson red. Barium, pale green, or we can say apple green, or apple green. For calcium, it is brick red, and for copper, it is blue green. So it is clearly mentioned the colors of these 4 ions over there. So we can say that this is 4. All right, the answer is 4, 1, 2, 3, 4, based upon the NCERT qualitative analysis, the flame test portion given over there. Let us discuss the next. Next question, 2-chlorobutane plus Cl2 gives C4H8 Cl2 isomers. Total number of optically active isomers. Okay, so basically we are performing the monochlorination of this compound. So this is butane, 1, 2, 3, 4. This is butane and 2-chlorobutane, right? What we are doing, we are performing the chlorination, the monochlorination. Now let us see how many positions are unique for this substitution. This position, this is also different, and this is also different. So let us substitute chlorine over these 4 positions. 1. This is 2. Then 3. And let us substitute over there. 4. Right? Let us see the chiral centers. How many chiral centers do we have? So we have the chiral center over here. We have the chiral center over here, and this too. Here we have this, and here we do not have any chiral center. So the question is total number of optically active isomers. Okay. So we get 2 from here, the D and L form, pair of enantiomers. We get 2 from here, right? 1, 2, 3, 4. And here we have the 2 asymmetric carbon or 2 chiral centers. Now this is something like tartaric acid. So we have the mesotartaric acid and we have the D and L forms of the tartaric acid. So we have 3 types of isomers over here. We can have meso, we can have D form, and we have L form, right? But meso, we know that is despite of these asymmetric carbons, it is optically inactive because of the plane of symmetry. So we are negating it. So 2 from here. So we have 1, 2, 3, 4, 5, 6. So the answer is 6. I hope this is clear. Let us discuss the last question for today. The question is number of spectral lines obtained in helium spectra when an electron makes transition from the 5th excited state. Now the 5th excited state means we are saying the higher level, that is, let's say N2, which is 5th excited state, that means it is 6. N2 is 6, and the N1 is first excited state, that means N1 is first excited state, that means N1 is 2. Now there's a formula for the number of spectral lines. We can simply use that formula, that it is N2 minus N1. We have N2 minus N1 plus 1 upon 2. Or you can see this is nothing but 6C2 only. This is 6C2 only. Permutation and combination we are familiar with. So this is 4 into 5 upon 2, and this gives us 10. So 10 is the answer. So number of spectral lines obtained in this spectra is 10. Number of lines are 10. So I hope this is clear. Okay. Okay then. Thank you so much. To take care.